So, our today lecture is about correlation and regression. I'm going to explain that how does it work. So, first we talk about correlation and then we'll be talking about regression. So, to start with correlation, we first need to discuss the scatter diagram. What do we mean by scatter diagram, or what do we mean by scatter plot? So, it is a simple graph of order pairs, because when you find regression or correlation, you will be given two variables, one is x, the other one is y. One variable will be considered as a dependent variable, whereas the other one will be considered as independent variable. So, for a scatter plot, it is just order pairs which are plotted in xy plane or in a coordinate plane, right. For example, you see, if I just give you a simple example, in that case, you see, let's suppose we'll be having x-axis, we'll be having y-axis, you have some values of x here, you have some values of y, right, and so on. There might be in the repetition of values of y as well. For example, for 1x1, we may have something y1, so we'll be simply point dot here, right. We may have for x2, let's suppose there is some value lying here, something like that, it might be y2. We may have another value for the same value of x, this one as well. And then we have for x3, we will be simply having something like, let's suppose that is here, okay. And then for x4, there might be something like this point here and this point here, right, and so on. So, in similar way, we can have many dots here, you see, okay. So, that is known as scatter plot or scatter diagram for a certain amount of data, okay. And obviously, what is the advantage of what is the purpose of scatter plot? Scatter plot is basically giving you a general behavior of the data, whether the data is linear or it has a linear behavior. We do not talk about that linearity, not exactly the linear, we are talking about linear behavior, okay, whether the data has a linear behavior or whether the data has a non-linear behavior, whether the data has an increasing linear behavior or it has a decreasing linear behavior, something like that. This one is an increasing linear behavior, whereas this one is a decreasing linear behavior, right. We will be talking about obviously three different type of linear behavior. In one case, we will be saying strong positive linear behavior. We will be talking about strong negative linear behavior, or we will be talking about something like that if you have a data type like this or maybe like this, right. In this case, this data will be having a weak linear behavior, okay. Obviously, that could be positive, that could be negative as well. So, if you have a data of this type, so it is a positive and weak linear relationship, but if you have something like that, so in that case we are having weak and obviously negative linear relationship in the data for x and y. If you have this one is x and this one is y, it could be the other way around as well. You may consider x as independent and y is independent as well, depending upon the nature of the data, okay. So, if you consider this data, let's suppose for a certain car rental companies, if you take this data, let's suppose there are 6 companies, company A, B, C, D, E, F, and the number of cars with each company, there are 63 multiplied by 10,000, it means 630,000 cars with company A, and their revenue is $7 billion, whereas that B has a 29 multiplied by 10,000 cars, and they are basically earning $3.9 billion. So, we may consider this one as a x and this one as a y, and then we go for the scatter plot or we go for the scatter diagram, okay. So the scatter diagram in this case is simply, we see that for each number, the value of x, which is the number of cars in 10,000, and that is the revenue which is given in billions. So we see that is the graph or scatter plot for the given data. And you see in this case the data has a linear behavior, because that can be maybe approximated by a straight line. Okay, so this one has a positive linear relation. Okay, we can consider that's a strong positive linear relation. Okay, so if you talk about this data, in this case we are basically considering number of absentees of certain students in a school or in a college, and there are final grades as well. So if a student A has 6 absentees, so his final grade is what? That was 82%. If he has a 2 absentees, so it is 86%, and so on. Okay, so for the scatter diagram, we see that for 2 there are obviously something like 86% of grades and something like that. You see, so in this case again the data has a linear relation, and obviously it's a slope, the line will be sloping downward, so it means this data has a strong negative relationship. Okay, and if you consider the relationship between the age and wealth, so the data is taken here from this Forbes magazine for a certain person with their age and having net wealth. So person A, whose age is 73 years, and he is basically having $16 billion. That's the net wealth of this A, and the same thing for B, C, and so on. So if you draw the plot of it, obviously we're taking the ages on x-axis and their wealth in billions on y-axis. Okay. So in this case, we see that the data has a very weak linear relationship. Okay, because you see that data can be represented by something, a line which has almost parallel to x-axis and it's sloping downward. So this one has a very weak linear negative relationship. Sometimes we do have data which has a non-linear behavior as well. So you see in this case, you see if you want to check its linear behavior, the linear behavior might be very weak, but its quadratic behavior, or maybe, yeah, this is the quadratic behavior of the data, so it is non-linear as well. So we can have a non-linear regression as well. So we'll be talking about that later on. So this type of data, it has a non-linear behavior. Now that was geometrically explained. How do we see the behavior or linear behavior of data? If we want to quantify that thing, we want to find a numerical number which basically tell you the strong linear relation or weak linear relation, so that can be found by using correlation coefficient. So what is the correlation coefficient? Is basically measure what? It's measure the direction of a linear relationship between two quantitative variables, right? Because we are basically finding this quantity, or we want to check whether this characteristic, the linear relationship, can it be quantified? So the answer is yes, it can be quantified by using correlation coefficient, right? We use two different type of samples for it. You see, if you have sample data and you want to basically find a correlation coefficient, so we represent that by what? We represent that by R, and for the population data we denote that by rho. Now keeping in mind that this correlation coefficient is always between -1 and 1, that means R absolute is less than or equal to 1. Okay. Now if the value of R is close to 1, it means the data has a strong positive linear relationship, right? And if R is close to -1, right, in that case the data will be having strong negative relationship. Okay, and if r is close to 0, that means the data has very weak linear relationship. Keeping in mind, if r is 0, that means there is no linear relationship, right, or very weak relationship. But that is a linear relationship. There might be possibility that if the linear relationship is very weak, there might be non-linear relationship which will be very strong. Okay, and you see that can be observed in this figure as well. If there is no linear relationship, it may the value of r will be 0. If there is a strong positive relationship, the value of r will be close to 1. And if there is a strong negative linear relationship, so the value of r, that will be close to -1. And if it is close to 0, so there will be weak relationship in the data. In this region, there will be negative weak relationship, while in this region, there will be weak positive relationship, right? So how do we find it? So let's have a formula for it. So the general or basic formula for correlation coefficient, that is what? It's simply the ratio between the covariance of x and y and the product of their standard deviations, which could be obviously written in this form as well. You know, covariance is defined as summation x minus x bar into y minus y bar divided by n, whereas this can be defined as summation x minus x bar square divided by n, summation y minus y bar square divided by n as well. And then we can cancel n with each other, where n is the number of points, or the number of data points. Okay, this could be used as well, but you can use this short formula as well for finding correlation coefficient. That is, this is obviously derived from here. If you multiply them together and replacing x bar by summation x by n, y bar by summation y by n, and then if you simplify it, you'll be getting this formula as well. This formula can be used if you want to find all these quantities using calculator directly. So that can be done. Okay. So we will be using this formula, simply sum of the product of the values of two variables x and y, and the product of their sums. The same thing, sum of the squares and the square of the sums, and for the data x and for the data y. When you simplify this quantity, you will get this thing, right? Okay, so let's find these quantitative values for the data we discussed a bit earlier. Before going to that, let's have geometrical representation of data and corresponding value of r. You see, this data has a linear relationship, but there is a very there is a spreadness in the data as well. So in that case, you can say that this r could be close to 0.5 somewhere. Whereas in this case, the data is again, it has a linear behavior, okay, and most of the data may lie along this line. Okay, so in this case, we say that if we draw a line here, so most of the data is lying along this straight line. So it means the data has a strong linear behavior. Okay, and once if you have this type of data, and in this case, you see the complete data is lying on the line and this line. Okay, so that's why its data is completely linear. So r in this case will be +1. The same thing for this data as well. You see that the data is obviously along this line, but there is a spreadness as well. There is obviously maybe high residuals in the data. So in this case, we have, and sloping downward, right? So we have r should be close to -5 from there. Whereas this data, again, it is lying along this line, where obviously the data, most of the data points are along close to this line. So and the line is obviously sloping downward. So we say r will be close to somewhere -0.9. Okay? Whereas this data is lying exactly this line, which is sloping downward. Okay, and that's a linear, obviously. So in this case, we say r is what? That will be -1, because the data is along that line, and the data is completely linear and it is sloping downward. So its correlation coefficient will be negative. Okay, so let's find these correlation coefficients for the data we discussed earlier, whose scatter diagrams or scatter plot were plotted a bit earlier. So if you have these companies, it's the same data we had a bit earlier. So we call this one as x, the number of cars, and the revenue we call that y. So we need to find the product of these two columns, which could be done by using calculator directly. So simply multiply these two together to get this column. Then you can take square of the first column of the values of x, or you can take square of this one, and then you find the sum. Because if you remember the formula, it contains all these quantities: summation xy, summation x multiplied by summation y, and summation x square and summation y square. So all these values are what they will be using in the they will be used in the formula. So we have the formula, that is n summation xy, the short formula we are using. So you would know how to find this summation. So you can simply find this summation x, summation y, adding them together. This summation xy, because you multiply these two columns to get this value, and then you add them. And similarly, if you take square of this one, so we have this data. For the y square, we have this one. We are only required to have these summations, okay, because the formula contains sum of all those values. And what is the value of n? That is basically the number of observations: 1, 2, 3, 4, 5, 6. In this case, n will be what? That is 6. Okay, so putting these values in this one, you see the n time, that is 6 times 682.77 minus summation x, summation y, that is 153.8 and 18.7. So multiply them together, divided by square root of 6 into summation x square. This is summation x square minus summation x whole square multiplied by summation y square in this one. So when you simplify this quantity through by using calculator, so this is what? This is simply 0.982, and we already have seen in the scatter plot that data has a strong linear positive relationship, because in this case you see the value of r is very close to 1. We are in the second example in which we had absentees and final grades. So for that purpose, again we take the number of absentees as x and the number of grades as y. So again you'll be finding the product of these two columns. You'll be taking square of this one, we'll be taking square of this one, and then we take the sum of all of them. And if you put the value in the formula, so we get what? We have minus 0.944, which is obviously a negative number, and that scatter plot, you might have seen that the line was sloping downward. So we have a negative correlation coefficient in this case. It means the data has a strong negative linear relationship. Okay, negative or positive relationship, that basically means if you are increasing one quantity, the other one will be increasing, and if you are decreasing the one quantity, the other quantity will be decreasing as well, if it has a strong linear relationship, positive linear relationship. And when it has a negative linear relationship, in that case, if you are increasing values of x, the values of y will be decreasing, okay, linearly. And similarly, if you are decreasing the values of x, the values of y will be increasing linearly. Okay, so that's why we are usually interested in both, that whether it has a negative relationship or a linear relationship or positive relationship. And whereas in a third case, where we had a data for age and wealth, and again you see in this case the value of r is very close to 0. You see it's minus 0.176, right? That's the quantitatively we see that the data has a very weak negative relationship between the two variables. Okay, now we talk about a regression. What is the importance of regression, and why do we study regression as well if we know interpolation? So you should know what is the difference between regression and interpolation. Okay, so in interpolation, usually when we have 2 points, we will be simply fitting that data by a straight line. Mean to say we have to use a polynomial of degree 1, because we know that a straight line can pass through 2 points. So we can have a straight line which would fit this data, right? So in that case, what is it? That's the interpolation, which is obviously linear interpolation. So for linear interpolation, you need to have 2 points. Whereas if you have 3 points, Then the question is, can we fit that by a straight line using polynomial interpolation or interpolation polynomial? The answer is no, we cannot do that, right? Because we cannot have a straight line which can pass through 3 non-collinear points, right? So in this case, if you want to find interpolation, so that must be some sort of quadratic interpolation which can pass through all these points. Okay, and if we have let's suppose n points, if there are n points, in that case you will be having a polynomial of degree n minus 1, right? If there are n points, you will be having a polynomial of degree n minus 1, which will be fitting the data. As I said, if you have 2 points, the polynomial degree will be 1. If we have 3 points, the polynomial degree would be 2, and if you have 10 points, the polynomial degree will be 10. Okay, that's one thing. Secondly, if you find interpolation for certain data points, okay, something like that, so the geometry of that polynomial must be passing through all the points. Okay, that's obviously important for it, because once you have a polynomial Pn minus 1, so this Pn minus 1 must be satisfied by every value of x. If you put x equal to x1, you'll be getting y equal to y1. If you put x equal to x2 somewhere, you'll be getting y equal to y2 here. If you put something x3, so you'll be getting y3, and so on. So all the data, given data, will be satisfied by what? By that polynomial. Okay. Whereas in case of regression line, if you have obviously 2 points, you can fit that by a straight line, and that is same as what we had in case of interpolating polynomial. But if we have 3 points, right? If you have, let's suppose this is 1 point, even though if they are non-collinear, we can still find a regression line for it. Okay, and if you have, let's suppose, anyway, any number of points, maybe let's suppose 1 point is here, even though you can have a repeated values as well. Next point is here, you can have this value, you can have this value, you may have this one, and so on. You can have such type of data. But now the number of points, they are 6 in this case, if you see, but we can still fit that by a straight line. Okay, that's the difference between the regression and interpolating polynomial. Okay, right. The second thing is it's not important for a regression curve that it must pass through the given points. It's not necessary for the regression line. It is important, it is necessary for the interpolating polynomial that it must pass to the it must satisfied by the given data, whereas in case of regression curve, it may or may not pass to the points, or that regression equation or regression curve may or may not be satisfied by those points. That's the main difference between what? Between regression and interpolation. Okay. So let's talk about it. Now, when we say I'm looking for a regression line, so if we, let's suppose we have this type of data, right? You see, there are many points, there are many data points for x and y. You see, these values are repeated, these values are repeated as well, these values are also repeated, but may have repeated values as well. Now, how many lines we can pass through these points? The answer is infinite, because you can have any type of line which can fit this data. But we are usually interested in best fit. Now the question is, what do we mean by best fit? Okay, best fit would be something like a line or a curve which passes through all the points, which is obviously not possible for a regression curve, that it may pass through all the points. So we will be looking for a line which is very close, right, or which is an optimal distance from all the points or all the given data. Okay, in other words, we may say that if we have this line, if this is, let's suppose, our best fit, let me assume that this is my best fit. If it is my best fit, then we have two types of point for all values of x. This is our best line, so let me just mark it with that something so that we may see. So if we take this point, we consider this point, that is for some x is equal to x1, right? This is for some x1, there is a value of y1. Okay, this is, let's suppose, y1. Now we have this value is known as observed value, whereas this value, which is lying on the regression line, this is known as predicted value. Okay, that's the predicted value. That's the value we usually what we predicted. And whatever about this values, so this is the given data, which will be considered as observed data. So these are basically the observed values, whereas the corresponding point on the regression curve, that will be what? That will be the predicted one. And we are basically interested to find the difference between these two, that is usually labeled as residual. Okay, that's basically what, if we have represented this point by y component, that is, let's suppose, y dash, where this is y1. So we will be looking for the residual between these 2 points, it's y1 minus y dash, maybe y1 dash. Okay, so this quantity is basically known as a residual, but we will be talking about you may go for absolute residuals, right? We don't care whether this predicted value is above the observed one or observed is above the predicted one. So we'll basically measuring what? Taking the difference between them. Okay, and then we basically you see, sometimes for some points the distance from this line will be minimum, whereas the distance from another line might be maximum. For another point, the distance from this line will be minimum, and for the other one will be maximum. So we do what? We basically take sum of all those values. You have to basically minimize what? Sum of these values. Okay, we may take residual and then we minimize this one. If this value is at the minimum stage, we say for any certain line y dash, we say that that line will be the best line. We use simple sum of residual as well for finding a straight line, and we also use sum of squared deviation as well as SSD. Sometimes we minimize this function, sometimes we minimize this function. It's basically simply that taking the square of these differences. Okay, I'm showing geometrically what do you mean by taking square basically, and which region or which area we want to minimize in that case, right? So yeah, so let's move further. So that's where I explained that this is the observed value. If this is my predicted line, or this is my best fit, so I'll be talking about what? We'll be talking about the distance between the observed value and the predicted value. The same thing for the next point, the same thing for the next point, next point. This point is already on the line, so the residual will be 0. This d3 to 2d will be 0, and so on. So we basically take sum of all those things. If you are using cost function as simply the absolute of residuals, okay? But we do take SSD as well. So if you take SSD, so what does it mean? And if you take residual, then what do we do? I'm basically taking you to the an external link, right? Just to show what does it mean basically. So okay, let's go out of this one. So I might be going to the external link. So yeah, where basically we have this simple animations. So let's suppose we consider any data, maybe height against shoes. So that's the basic data, which is a scatter diagram for this data. Okay, and we can have different lines from here. You can change the value of A, you can change the value of B, because you know the straight line is equation y equal to ax plus b, or you may write y equal to a plus bx, where A is representing slope of the line, where B represent the orientation along y direction, or maybe just translation along the y direction. So if you see, if you change this translation and slope is 0, so what is going on? We are having basically a straight line. We can have a positive slope, so you see this one. You may bring it a bit down, and then you see we can have this one. Okay. Now you can have a squared residuals, or you can have simple absolute residual. You see that is showing what? That's the distance between the values. If I just change these things, you will see the residual will be changing. That's the differences between obviously between the actual between the observed value and the predicted value. You see, if you change this one, you may change the position as well. Accordingly, it will be increasing. Okay, and if you go for the square residual, in that case, what would happen? We'll be basically drawing a square here, whose length or width, whatever, both will be same. That will be the distance of predicted value from the observed value. You see, if you simply take this line here, okay, this one, so this is the width, and then we draw a square. Okay, so I'm showing that in this one. You see, if you look at the one point simply, let's suppose we look into these 2 points. So what would happen if I just remove the line, move the line away from the points? You see, you'll be having different squares. As we come closer to the points, you see the area is getting closer towards the 0. This is the sum of the areas of all those squares. Okay, so you see that is basically known as the best fit. So in this case, the correlation coefficient is 0.85, which means close to 1. So there is a strong linear relation. And if you want to see the best fitting line, so the best fit line is simply this one. The red line is the best fit, which has a slope of 1.81 and 50.4. And if you see the sum of the residuals, so in this case the value is very close to 0. And if you talk about these residuals, so again obviously they will be close to, the sum will be close to 0 as well. Okay, so yeah, you can go for different type of data types. Spending against salaries, you can have mortality versus time, minimum wages against time, and then you have internet users and time. You can have any data to just see the best fit and anything, because you can have many lines in that case. Okay, right, so I hope it's clear to everybody now. Right, so let's move further, and now we talk about the determination of equation of regression line. That was geometrically I explained. So how do we do that quantitatively? So for that purpose, we are basically using this line, equation of line. Obviously you know that we are talking about regression line. So this will be y dash is equal to a plus bx. Okay, so y dash is a plus bx, right? That's a simple this equation of line. This is the y-intercept, and this is the slope of that line. Okay, where the y-intercept can be found by use this formula, whereas the coefficient that is known as slope, that can be found by using this formula. Now the question is, how do we find these values of a and b? I'm just giving you a few hints here. You see, we want to find the square residuals between the observed value, that is y and minus y dash. Okay, and we take the square residual, you see, then we will be having like y minus y dash, which is being taken as a plus bx, so we will simply take as a bx, and then we have square. Now what do? We would find basically the value of a and b, because changing the value of b and a, you'll be getting different type of straight lines. Okay, and we have to look for optimal values of a and b. So we need to minimize this cost function, this last function, whatever you call it. So we need to differentiate this function with respect to a first, its partial derivative, because we need to find the stationary points, right? So partial r by partial a, that will give you what? Just a power rule first, and then we have y minus a and minus bx, okay, multiplied by minus 1, because derivative of this with respect to a will be minus 1, and we do what? We equate that to 0, because we have to have a 0 first variation of the last function. And from here you may have what we have, we need to take summation as well, keeping in mind, don't forget that summation, because it's a sum of square residual. Okay, the same thing will be here as well, we will be having summation. So when you apply summation on it, what would happen? You can cancel 2 as well, right? And you can cancel that minus 1, dividing both sides by minus 2, so we get rid of this thing. Applying summation y, so we can have summation y minus summation a. You are adding a n times, so that will become simply n times a minus b times, b is a constant, and then we have a variable x, so that is summation x is equal to 0, right? Which basically give you what? A linear equation in a and b, which will be n times a minus plus, in fact, summation x times b, or b times summation x, that is equal to summation y. So that will become a first equation for us. Okay, that's the equation number 1 for us. Let's suppose we call this equation number 1. Now it will be minimizing this this r with respect to b as well, so we need to take partial derivative with respect to b. So applying again first power rule, so it will be giving you words 2 times, again summation will be there, and we'll be having y minus a minus bx, and then we have derivative with respect to bx will give you simply x here, minus x obviously, that you can again cancel it, minus 2 on both sides, and we'll be equating that to 0. Okay, we equate that to 0, because again we need to have both first order variation to equal to 0. So we take partial r by partial a 0 and partial r by partial b 0. So this equation obviously can cancel 2 on both sides, dividing by 8, and then multiplying x inside and applying summation as well. So we'll be having, from here we can write this equation in the form summation xy, see, summation xy, and then we have minus a summation x, and then we have minus b summation x square. Okay, because you multiply x inside, so we get x square, and that is equal to 0, which will be simply made as again to have another equation here. So we'll be writing that as summation x times a plus b summation x square is equal to summation xy. And we call this equation number 2. Now what do? We can simply solve these two equations for a and b. I hope you know how to do that through linear algebra, and by using simple multiplying this equation. If you multiply, I'm just giving you one step and the rest is straight simple algebra, you can do that. So if we multiply equation 1 with summation x multiplied by what? Multiplied by equation number 1. Okay, multiplied by equation number 1, and then we do subtraction and multiplying equation number 2 with n. It will give you the value of b. It's n times equation number 2. After subtraction, you will get the value of b. Okay, and then putting the value of b in equation number 1, you will get the value of a, and these will be the final outcomes, a and b. Okay, so that's the way to do it, and I hope it's clear to everybody now. Right, you may pause the video at the moment, and you can simply try this to get these values. Okay, so now we find the equation of a regression line for all these all examples we discussed earlier. So first we talk about the data given in car rental companies. So we need to find equation of regression line for that, and then we need to graph the scatter line and the scatter data as well. So we had already found that n was 6 in that case, and the summation was 153.8, and so on, so on. And putting these values in the formula discussed earlier, that was for A, it is this quantities. Keeping in mind, you will be taking equation of regression line in this form, y dash equal to a plus bx. If you take a formula or equation in the form ax plus b, obviously these two quantities will be changed. That will become b then, and this will become a. That you should note that, right? Because this is the slope formula, and this is the y-intercept for the regression line. Right, so if we take y dash equal to a plus bx, so this will be a, this will be b, and you simplify, it's 0.396, and this is 0.106. Okay, so that's the regression line, y dash equal to 0.396 plus 0.10x. Now if you put the observed value here, you'll be getting some predicted value which may be close to the observed value of y. You'll be putting the observed value of x here, and you'll be checking whether the values of y are close to those yi or not. Right? We usually represent this predicted value by y dash and the observed values by yi. Okay, so if the data has a strong positive relationship, in that case obviously the value of y will be close to, of y dash will be close to y as well. The next example was for absences and the final grades, and in that case we had, I think you can do that yourself. You may pause the video and then you should try these values. We had found these values a bit earlier with n equal to 7, summation x was 57. Putting all these values in the formula for A and for B, you'll be getting this one and this one. So you see, in this case we are having negative slope, because if the data has a strong negative relationship, negative relationship, in that case the slope will be what? That will be negative, okay? Because in that case the data will be lying down, sloping downward. So equation of regression in this case is what? 102.493 minus 3.622. Okay. And then next we talk about the coefficient of determination and standard error of estimate. Because it is basically used, why do we study a regression line? So regression line basically properly defining the data, properly explaining the data. If a regression line could properly explain the data, in that case we say that we will be having a higher coefficient determination. And if it's not explaining properly, in that case we say there will be a strong standard error of estimate. So they are basically used for whether the regression line is explaining the data or it is not explaining the data properly. Right. So let's suppose we first talk about what do we mean by that explaining the data or not explaining the data. So let's suppose let's have a hypothetical data, that is for x equal to 1 we have 10, for 2 we have 8, and so on. The corresponding regression line for this data is what? If you find that yourself, you should pause the video and find it. We can find its correlation coefficient as well, that is 0.919, which means there is a strong relation between the data, and so the regression line is what? That is 4.8 plus 2.8x, right? So in this case, the difference between the mean and the given observed value, and then we take square, this quantity is known as the total variation. And obviously sum of the square deviation of mean from every observation is called total variation, and if you divide that by n or n minus 1, then we have variance, and after square root we have standard deviation as well. Okay, and we are basically measuring the deviation from where? From the of the mean from the observed data. And if you do same thing for the predicted value, what would happen? We call this data as explained variation, right? So if this quantity is minimum as much as possible, so obviously you see that y dash is properly explaining what? Properly explaining the whole data. Keep one thing in mind, it must be noted that mean, that's y bar, for the observed data and for the predicted data, it is always same. In other words, we may say that y bar and y dash bar, they are always same. Now I hope you understand what do you mean by y bar. Y bar is basically the mean of observed data, whereas y dash bar is the mean of predicted data. So both of them are same. That's why for total variation and for the explained variation we are using y bar, right? Because they are same. And this is known as what? This is known as total variation. Right. Now most of the variations can be explained by that relation. Okay. So we, as I said, the value of r, that's coefficient of determination, that is if that is close to 1 or minus 1, at this moment we are basically r is the regression correlation coefficient. So if r is close to 1 or minus 1, right, the line, the regression line will be basically explaining the data properly, right? And that purpose we say if this value is close to this one, because you see if y dash is close to y, in that case these two differences will be close to each other. Okay, and it means that all the observed points are also lying on the regression line. Okay, and in that case y dash minus y bar square will be equal to summation y minus y bar, is y dash will be getting closer to y. Okay, and the quantity which is y minus y dash square, that is what? That is known as the square of the residuals, and this is the unexplained variation, because this is the difference between the observed value and the predicted value. So the difference between observed value, predicted value, that was termed as residual, and then we take it square and take summation, that give you unexplained variation. That's that part of the data which is not explained by the regression line. Okay, and keeping in mind that the total variation is basically the sum of explained variation and non-explained variation, unexplained variation. Okay, so that's geometrically what does it mean if we have a regression line. So for x bar, basically that will be coming on the y bar. Okay, so y bar is obviously same for both things. If you are predicted values or you have observed values, the mean will be here. Okay, and that will correspond to what? That will correspond to x bar. So that is y bar line. You see, if you take a point x here, so this point is what? That is basically x y bar. This is the predicted value y dash, and for x that is the predicted value, and this is the observed value for same x. You see. So from here to here, that is the total variation, because we are basically taking difference of y with y bar, and then we take square, and then we do that for all the points we are given. Okay, so that total summation will be giving you what? It will be giving you total variation. Whereas the difference between the predicted value and mean, that is basically what? That's the explained variation. taking square and then summation, that will be the square, that will be the explained variation, where the difference between these two, the predicted value and the actual or observed value, right, that is known as the residual, and then we take square of it and then you take summation, that is known as unexplained variation or unexplained deviation. Because you see, this is the part which is not properly explained by what? By the regression line. If this line is getting close to this point is getting close to this point, in that case we will be saying that unexplained deviation are getting close to 0, and in that case obviously the explained deviation will be getting bigger, and when this quantity is bigger, it means that your actual value or observed value is very close to the predicted value. Okay, and from here you can see that the total variation is simply from here to here, which is the sum of the explained variation and the unexplained variation. So from geometrically we can see that these two quantities, the sum of these two quantities give you total variation. The same thing can be done quantitatively as well. If we have this data, let's suppose, again it's the same hypothetical data for 10, for 8, for 12, for 16, for 20, we are having this y dash and so on. Y dash is obviously found by putting this value in the regression equation of regression line. Okay, so and then we find the difference between the predicted value and the mean. The mean is what? That's simply adding these together by dividing by 5, or adding these together and dividing by 5. Okay, and then you simply take the difference and you sum it, that is 78.4. So this is what? This is basically the explained variation. So explained variation in this case is what? It's 78.4. Now if you find y bar is obviously know that 13.2, whatever you find from here or from here, it will be 13.2. Now if you find total variation, subtracting this 13.2 from y and then you add them, so we get what? The total variation will be 92.8. If you square and then you add them, it will give you 92.8. Okay, and then we have unexplained variation, which is the difference between these two values, y and y dash, and then we take square of it, and then we take the summation. So that is 14.4 something. Okay, so if you add these two together, 14.4 and 78.4, that would give you 92.8, and that's obvious because total variation is numerically it's proved, or analytically it is proved, right, that sum of total explained variation and unexplained variation is the total variation. Okay, that's obviously done quantitatively. Geometrically we know that. Right, so this quantity is, I said earlier, it is known as residual. Then we take the square to make it obviously and then take the sum to have that unexplained variation. And if this quantity is going towards 0, if your predicted value and the actual values are same, or they are very close to each other, this will be getting close to 0. Now what is the coefficient determination? You see, the total variation and a specific part of that total variation is being explained. So how much fraction of the total variation is being explained? So that can be simply found as explained variation divided by total variation. You see, if you want to understand this in a simple steps, so if we have a total something 70, right, and one part of this, let's suppose you have to split that in 2%, one is A and the other one is B, right. So let's suppose A has taken 20 where B has taken 50, right. So what fraction of this total variation is coming into B? So you will simply find that 50 divided by what? By 70, and if you multiply by 100, so that will be converted into percentage. Okay, so you see that we are interested in what? Coefficient of determination, which is the ratio between explained and total variation, right. So we have explained variation divided by total variation. Explained variation was, for a previous example, 78.4, and total variation was 92.8, and when you find that, we get 0.845. Keeping in mind 0.845 is basically the square of correlation coefficient. Right. So if you have for that specific data we discussed earlier, okay, so that was 0.919, and the square of 0.919 is 0.845. So that's why we are having the same thing. Okay, so coefficient of determination is what? That is the ratio between explained variation and total variation. And then you see coefficient of determination is measure of the variation of the dependent variable that is explained by the regression line and the independent variable. For that purpose we are using r square. It means if r is close to 0, it means the regression line is not explaining anything of the data. Okay, but if r is getting close to 1, or because we are talking about r square, so r is getting close to 1, in that case we'll be saying that the regression line has explained most of the data. Because you see, in this case, if you have 80.845, it means that 84 or 85% of the data is being explained by that regression line. From here you can say that how much the regression line is the best one. Where the second part was what? That was sum of the residual squares, which was termed as unexplained variation. So the standard deviation of the unexplained deviation is called what? That is known as standard error of estimate. So standard error of estimate is simply summation y minus y bar square, y dash square divided by n minus 2. So this will give you what? This will give you basically the standard error of estimate. Okay, and if this value is getting close to 0, what would happen? It means that a regression line is the best one, and it is representing most of the data. And if it is getting bigger, it means the regression line has not properly explained the given data. So let's suppose we have this data 1, 2, 3, 4, 5, 6, 4, 4, and 6, and then we have corresponding values of y. We find the regression line, which is 55.57 plus 8.136, and then we simply find the regression line. Well, find the value of y dash, and then we have y minus y dash square to find the coefficient of determination, to find the standard error of estimate. So we have this value, and then we divide this by n minus 2 to get 6.51. So in this case, the standard deviation of observed value about the predicted value is what? That is 6.51. We can use another short formula for this as well. If you don't want to construct a regression line, so you can use this formula by replacing the value of y dash in this formula. In the previous formula, you have this formula. See, so we can simply replace that y dash by a plus bx, and then you can take the square and simplify it, and then you'll be getting this formula. You can use this formula as well. Here is the example for it, and you see in this case the same formula, the same data is used, and a different formula in this case to get that standard error of estimate is same as 6.48. Okay, so that's the way to do to use regression line for representing the data, for predicting the data available at the present, and you'll be predicting the data for future as well, or for past as well. Okay, so thank you very much for today's lecture. See you in next video with something new and something more interesting. Thank you very much.